Good morning, Math 8, and happy Friday. So, we are going to keep talking about systems of equations, hopefully getting a little bit more towards the behavior of graphs, but really focusing on tables and real-world applications and what is actually happening when two lines intersect. So we're going to talk about two bugs passing in the night, a ladybug and an ant. And I'm going to keep on with my color coding just to help you understand there are two totally separate things going on here. So ladybug and an ant are a certain distance apart, and they start walking towards each other. The graph shows the ant's distance from a starting point over time. So the graph shows the ant. The ladybug starts out 25 centimeters away from the ant, but walks only 1 centimeter each second towards the ant. So the ladybug starts out 25 centimeters away, walks 1 centimeter each second towards the ant. Okay. And then the ant, we'll do the ant in purple. The ant is already on the graph, so the graph shows the ant. So we want to think about what we can get from the graph of the ant. So the ant, let's see, I'm looking at my points, I'm looking at 1 second. So in 1 second, the ant goes 4 centimeters. All right. So that's my information I have for my ant. All right, and I guess we'll come back to that later. So let's look at our questions in a row. Draw the graph of the ladybug's movements on the graph. Okay, so ladybug in pink. So where does the ladybug start? The ladybug starts 25 centimeters away, and it walks 1 centimeter each second towards the ant. So take a minute and visualize what that's going to look like on the graph. Starting out 25 centimeters away and walking 1 centimeter each second towards the ant. So that 25 centimeters away is going to be our y-intercept. Ladybug starts out way up there and walks 1 centimeter each second towards the ant. So after 1 second, it gets 1 centimeter closer. Ladybugs walk fairly slow, if you've noticed that. So 25, 1 centimeter closer in 1 second. All right, so then 1 second later, it gets even closer. And then 1 more second later, it gets even closer. So I can see what's happening here. And some of you are ahead of me and thinking, oh, look, that's where they intersect. That's what we've been looking at this whole time. So there's my graph of my ladybug. I'm just going to draw some. Ooh, that was not a straight line. That was terrible. Oof, these are awful. Oh my goodness, let's draw it out. I could blame it on being Friday, but it's actually Thursday when I'm recording this, so I can't blame it on Friday. So, let's see. We drew the graph of the ladybug's movement on the graph. Write an equation representing the relationship between the ant's distance from the starting point. That's written wrong. I'm going to fix that on yours. Between the ant's distance from the starting point and the amount of time that has passed. And there's another typo down below, but we'll get to that later. So we want to write an equation about the ant, who's purple. And the ant is this guy. So y equals mx plus b again. We want to think about what's our slope or our speed and our starting point. Take a second, think about it. Okay, so for my ant, we talked before about the ant's graph, and the ant starts out at 0. He starts out at his own starting point. And every second, the ant goes 4 centimeters. So 4 centimeters in 1 second is just 4 centimeters per second. So his equation is just y equals 4x plus 0. Or you could just write y equals 4x. So how fast is the ant walking? Well, we already talked about that. 4 centimeters per second. That's really a better question to ask before number 2, because we used that speed to get us our graph, or our equation. So there's the ant. Now I want to write an equation representing the relationship between the ant's distance from the ladybug starting point and the amount of this is another typo. So I fixed it on yours, but the equation should say is write an equation representing the relationship between the ladybug's distance from the ant's starting point. And this is all better on yours, I promise. I've already fixed it. But see, this is so nice because now when I see a typo on my video, I can fix it before you ever see the assignment. Ladybug's distance from the ant's starting point and the amount of time that has passed. All right, so we're gonna look at the pink line now. So you wanna think about where does the ladybug start and how does the ladybug move? And we're gonna notice here, the ladybug's moving towards the ant's position. It's towards the ant, so its slope is going to be negative. So take a minute, think about what the slope is going to be. So we should already know the slope because we know the ladybug's information up here. The ladybug starts out 25 centimeters away from the ant and walks 1 centimeter each second towards the ant. So the equation is going to be y is 25, the distance is 25, minus 1 centimeter each second, so 25 minus 1x. So there's our equation for ladybug. And this isn't super like our goal is to review writing all this stuff. Our goal is really to think about these equations together and what their intersection points mean. So question 5 is our real like go-getter question. Sorry if you can hear my kid singing. He's home alone with me at the moment, so he's just running around singing. When will the ant and the ladybug meet? How far will they be from the ant's starting point? So look at that graph. How long will it take until they meet, and where will they be? Hopefully you're zeroing in on this point right here, because that is our intersection point. They will meet after 5 seconds. They will both be how far from the ant starting point? 20 centimeters from where the ant started. They certainly didn't have a meet me halfway kind of deal, did they? Oh, that would have killed it in the classroom. No, it wouldn't have. It's okay. I thought it was funny. So they will be 20 centimeters from where the ant started. All right, so that's our solution. They'll be 5 seconds have passed. They'll have been walking for 5 seconds. And after 5 seconds, they will be 20 centimeters away from where the ant started. So there's our solution to our system. All right. Okay, so next we're gonna look at when a couple funny things happen on graphs sometimes, and with systems of equations, a couple special cases, if you will. So once you get to special cases, you know we're kind of nearing the end of the unit. And we're not really nearing the end of the unit, because there's still a lot more things we could do, but some of them just aren't as good to do over distance, so. We're looking at a close race here. Austin and Jackson were racing 60 meters on their bikes. Both racers started at the same time and rode at constant speeds. So here's a table that gives information about Jackson's bike race. Okay, so we're gonna go ahead and give Jackson purple. All right, so we're gonna plot these points. He started at 0. And then, okay, I gotta scale this graph. Okay, 0, 6, 9, and that's going, well, the race is 60 meters. So let's see, I'll make this up to 60. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. There's 10 boxes. So I'll just make that 60, and I'll count by 6s. So 6, 12, 18, 24, 30, 36, 42, 48, 54. And then here is 10 across. I can just count by 1s here, we'll be fine. Okay, so we'll plot Jackson's points. He's at 0, 0. Then he's at 6 seconds, he's at 36 meters. So 6 seconds is at 36 meters. And then after 9 seconds, he's 54 meters. So there's his graph. All right. And he rode at a constant speed, so we could use a ruler if I had one, or I'm just going to use this 3-hole punch to connect all my points. And my child is yelling my name, so hold on. Okay, sorry about that. So I've used my straight edge to connect Jackson's points. So we're done with that one. Let's look at Austin. Tell us anything about Austin? No, he's a mystery. Austin traveled the entire race at a steady 6 meters per second. So, okay, 6 meters per second. That means that Austin, after one, I'll make a table of values. Oh, geez, I should be doing this on the fly. Yeah, do seconds and meters. So at 0 seconds, he's at 0 meters. He still starts out at the y-intercept. But if he goes 6 meters per second, that means every second we add 6 meters to the distance. So he goes 6 meters per second. In 2 seconds, he's gone 12 meters. All right, so he's got 0, 6. I'm sorry, 0, 0, 1, 6, and 2, 12. After 3 seconds, he's gone 18. And you can sort of get the picture from there. And the interesting thing here is that for this race, these two are neck and neck. They are the same lines. They are the same distance away, always. So they are the same line. So who won the race? It was a tie. Very sadly. I know. We hate ties. This line down here was my first attempt to draw Jackson's line, and it was really terrible, so please ignore that. I'm very sorry. No, I have erasable pens. I just don't use them. Why would I? So it was a tie because they were going the exact same speed. He was going 6 meters per second, and if we'd figured out Austin's, if we'd kept going, we'd see... I'm sorry, this is so messy. That after 6 seconds, Austin was also at 36 meters. So we would see that he also has that same 636 as Jackson had. Because also 6 times 6 gives you 36, and 9 times 6 gives us 54. These are just proportional relationships. So we can see that they are the same, in fact, relationship. So, here's another close race. All right. So let's see. Aaron and James are racing 60 meters on their bikes. Both racers started at the same time and rode at a constant speed. Here's a table of information about James's bike race. Okay. Let's see. They both race 60 meters again. I'm going to scale my graph the exact same way. Okay. So now let's see. The table gives information about James's bike race. So I'll do James, the table, in black this time. That's blue. I don't know what it is. They look very similar, honestly. This is blue. So, let's see. At 1 second, he's 0 meters from the start. You got a late start, apparently. At 6 seconds, he's 30. And at 9 seconds, he's 48. I'm not going to use 3-hole punch again. I'm just going to draw the line. All right, there's James. So we graph that. And then we know Aaron traveled the entire race at a steady 6 meters per second. Sounds familiar. On the same set of axes, graph the relationship between distance and time for Aaron's bike race. So I'll make a better table this time. So for Aaron, we will do seconds and distance. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 seconds. This is truly awful, but that's okay. So her distance, after all this time, again, 6 meters per second. So she starts at the starting line. Theodore, be quiet, please. Her distance starts out at 0. Let's see, add 6 is 6. Add 6 gets 12. So, she's actually driving the exact same pace as Austin was in the previous problem. Theodore! Shh. So we're adding 6 every time because she goes 6 meters per second. Let's graph these points. Dear heavens. So here's Aaron's line. Oh, I'm supposed to do hers in purple. That's okay. She'll understand. Aaron. So let's talk about these two lines. They're going the same speed. Look at this. James is still going 6 meters in 1 second. These lines are parallel. They're never going to meet. So it looks like she started out a second before he did, and they're just going the exact same speed. So it looks this time like Aaron won the race. And he is the same distance behind her at all times. All right, so I'm just noticing interesting things about graphs there. So this is going to help with the first part of the exit slip, and the previous part's more the second part of the exit slip. We're only going to do up through the equations. I think I'm pretty much done with the graphing because I'm not having you guys do a lot of graphing or any at all. So we are going to just look at this problem. So Nico and Hannah are drinking milkshakes. Nico starts with 12 ounces and drinks 1/4 ounce per second. Hannah starts with 20 ounces and drinks 2/3 ounce per second because she's got a bigger straw. A dunk in the large drinks get a better straw. It's probably like that. Or it's more delicious shake. So create a table to model each student's milkshake over time. So I'll just put Nico in purple because that's what I'm holding. So he starts out with 12. And then every second he drinks 1/4 ounce. So he loses 1/4 ounce. So I'm going to subtract 1/4 ounce. I'm just going to write them as decimals. No, I'm not. I'm going to do fractions. So I'll do 11 3/4, and then 11 1/2, 11 1/4, 11. And then I'll lose another quarter, 10 3/4, 10 1/2. 10 1/4, and 10. So we're just taking away 1/4 ounce every time. And if you want to do them as decimals, that's fine. You can do that. All right, and then 9 3/4, 9 1/2, 9 1/4, 9. Okay, so after 12 seconds, he's got 9 ounces left. So we're just following along with the same rule. Drinks 1/4 ounce per second. So that means we lose 0.25 every time. All right. So let's look at Hannah. Hannah starts with 20 ounces and drinks 2/3 ounce per second. All right. So again, I could do my calculator. I could start at 20 and subtract 2/3 every time. So 20 minus 2/3 would be 19 1/3, and bear with me as I do math in my head. 18 2/3 down to 18. And then minus 2/3, 17 1/3. Then I got 16 2/3, and then 16. So I'm losing 2/3 each time, or subtract 2/3 each time. So 16 minus 2/3 is 15 1/3. Minus 2/3 is 14, too many ones, and 2/3, and then 14. And keep in mind, we're looking for that point where these two are going to intersect. Have we found that point yet? No. We have not yet found the point where they will meet. But we're going to look for the time in the future when eventually they will have the same amount left. All right? So we'll real quickly. We'll do this on the graph. It'll be quick. So then Nico, I'm going to write an equation to model each milkshake. So y equals for Nico starts out with 12, loses, can you hear my child calling my name? I'm so sorry. 1/4 ounce per second. And then Hannah starts with 20 and loses 2/3 ounce per second. All right, so I just want to make sure that starting value is not attached to the x. And the rate, the per, gets the x. All right, so that's the important part about that. The rate gets the x, because that's what it's 2/3 how many times. They only start out with 12 once. So we're going to graph the long-term behavior of Nico's milkshake and of Hannah's milkshake. So you can plot the starting points. So Nico at 0 seconds was at 12. And honestly here, I'm going to graph the big numbers, like 0 and 12, 4 and 11, 8 and 10. Oops, that was not right. That was right. And then 12 and 9. Those are the big numbers for Nico. And then that will continue with a straight line pattern, which I can draw here, mostly. And then Hannah starts at 20. And again, I'll plot the big points for Hannah as well. I'll plot the 20, and I'll plot the 3 and the 18. She's got more convenient intersection points than he does. 3 and 18. And notice her slope was negative 2/3, so her graph goes down 2 and right 3. So down 2, right 3, down 2, right 3, down 2, right 3, down 2, right 3. And we see that, 6 and 16 was one of her points. So 6, 16, 9, 9, 14. So we're seeing all these big points. So down 2, right 3. Oh, she almost caught up here. Down 2, right 1, 2, 3. Oh, looks like they passed at some point. Look at that. So you can actually see on this graph where they will cross. So where will they meet? And again, it's a little bit approximate. It's at around 19 minutes. So it's approximate. So the solution, I'm skipping 10 for now. So the solution is about about 19 minutes. And they will both have, what is that, like about 7 1/4. So at 19 minutes, oh, there's Sebastian waking up. At 19 minutes, both kids will have about 7¼ ounces left in milkshake. All right, so the X value is about 19, a little bit more. I can say 19.5 if I wanted to. You don't have to, it's about 19. And after about 19 minutes, both kids will have about 7¼ ounces left in their milkshake. So can we determine from the graph when they're gonna finish their milkshake? No, not yet. Okay, so that should be plenty to get you started on the exit slip. Again, nothing's graded yet. I'll keep my graded assignments real simple. If it's a little bit confusing, I do apologize. It is tough to do without being there in person, but hopefully the realistic context is helping you to sort of grapple through it. Please ask questions if you need. Please email specifics. Don't just say, I'm confused. Email me specific questions. I was confused on the Nico Hanna example, or I was confused on the races. All right? Great work, and give your exit slip a good try.